and we can it's 35 past 8, and let me share my screen as well. So are you able to see my screen?
Yes, sir.
Okay, that's nice. So I think I shared this file with you, and I will make a little bit large so that you can view the things, right? Okay, so let's start this session, and I will just make you go through the very basics, and then we will slightly slide walk through critical part of the topics, right? So if we go with the objective of this particular class, or you can say lecture, our purpose is to understand various structural form. That is, you should know what is beam, what is plane truss, what is space truss, plane frame, space frame, arches, cable, plates, shells, right? So these are the various forms once you come across with your structures, right? We will also see what is state and use of condition for static equilibrium. We need to understand what do you mean by static equilibrium. Further, we will calculate the degree of static, right? And kinematic indeterminacy. We need to feel them in order to understand these two different aspects, right? Degree of static. What do you mean by static indeterminacy? What do you mean by kinematic indeterminacy? So most of the analysis is based on these two deterministic, right? So one is force-based analysis, and another one is displacement based analysis. So slowly you will categorize these things. So tell me, how many of you know that these are categorized based on these two criteria? Just type in a chat box and I will understand. Did you aware that there are two different types of analysis? You have a force based, and you have another one is displacement based.
This is new to me.
So once you start your analysis, you didn't aware of these two types in your STY?
I mean, I will say I wasn't aware of them, although we used them, yeah, for sure. But I wasn't aware of the difference and identifying them as two different
Oh,
concepts.
okay. So actually, whenever we start analysis, there are various, like once you start, like your moment distribution method, your slope deflection method is a displacement based analysis. Your moment distribution is force based analysis. I don't know um, how you have been taught, but it's fine. I'm not going back. I'm just making you aware, right? So if you see this, once you find this static criteria and kinematic criteria, you will come across with these type of analysis. And if you further advance, you will come across two things: flexibility method, right? Sorry, flexibility method, and then stiffness method, right? So yeah, one is again force-based method, and stiffness method is your displacement-based method, right? Of a given structure such as beam, truss, frames, and further we also know whether it is a stable structure or whether it is unstable structures based on these conditions, right? So there are a lot of things once you start your analysis in order to see your structures, your different type of supports which has been provided to the structures, whether they are okay or not with the structural thing. Means you can't provide so many supports in a structure. You need to be stable. You make them in a equilibrium conditions, And that's what structural engineers generally do, right? Further, that is what I'm saying. Further, once you define all these, we will see what is a flexibility and stiffness coefficients. And we will also see force displacement relations for simple structures. And you're already aware of how the load transfers from one to another element in the structure. So this is what we are going to learn in this particular topic, right? So this is just an introduction about how, means, since the beginning of human race, I can say we are always try to build something, right? So we always initially we don't know like theories, etc. But yes, we do know how to make them stable and how to make them stay for longer. So that is what our civilization start with. So if you see an example of pyramids construction in Egypt, like if you see some of the YouTube videos, you will see how accurate their dimensions and angles are. So they know the accuracy of these structures, and still they are staying after like 2000, more than 2000 years, right? And these are the masters builders of that civilization, and still these things still exist. And further, if you see, there are Parthenon at Athens, that is 2005 years old. Then in Stupa at Sachi, it is 2000 years old. Castle of Good Hope is 380 years old. Eiffel Tower 120 years old, and many more. So if you draw a timeline like this and you just picked some of the structures which are drawn, which were built during the life, or you can say human race, you will come across, yes, craftsmen or engineer do exist with time, but yes, as we move towards more modern era, we know much in depth of various type of techniques which we are to solve different types of problem within an economical way. Means if you see many old structures, the wall are quite huge, right? In order to take care of most of the tension generated in the structures, right? So they arrest all those stresses inside the structures, so you don't see any formation of cracks outside of the structures. So tell me, how many of you know that many of these structures are shaped in an arc, right? To take care of all the loads from the top. So what is the purpose of arches? Like I hope you have studied to solve um, two pin arch and three pin arch. Did you do that in your previous classes? How to solve arches? Yes. So tell me, what is the purpose of arch, Ethan? Can you speak on that? Just
Can you
tell me
hear me?
something about arch.
Hello, sir. Can you hear me?
Yes, I can hear you. Perfect.
My memory is a bit fuzzy, but is it that the shape of the arch allows for the top or the top forces to be transferred to the foundation easier?
Correct. I'm very much agree with you. But what type of forces generally arch have, which they transfer? What they do basically?
Is this
What is the
uh,
nature of force? Okay, tell me the nature, whether it is tension or compression. How the
oh
arch is like.
it it keeps it uses compression to keep the shape, sir.
Correct. Very correct. I agree with you. Angelina, do you want to add something in this?
No, sir. I was just stating the nature of forces.
Okay, perfect. And that's good. Let me use a little bit of whiteboard right? And then we can just have a little discussion on this. So I'm just saying why these people are so eagerly or so nicely use all those shapes of arches. Like I recently on a research visit to Granada, Spain, and then I see a lot of horseshoe type of arches, like this one. Okay, and many of them are like even this one, right? Yes, so the purpose of such shape of arch is definitely not to create tension, right? In life also, if you have a tension, definitely you will not move good or forward in a better way. But similar for the structures, they structures don't like tension, right? And that's what, whenever there is a tension, we need to use reinforcement, right? And if you see all these old structures, they don't have much reinforcement in their structures, like building them. They try to arrest those tension in form of either shape or in form of either width, right? They increase tremendous width, like a meter or more than a meter or half a meter, in order to arrest all those tension inside the wall. So even if you see any old structures, the purpose is to give such shape, because if you use a flat beam, what is going to happen? You have a bottom part will be bottom part will be in tension, right? And top part will be in compression if we apply load vertically at the top, right? So that is what. So what we use is, we try to, whatever the moment shape, if you draw a bending moment diagram of any such beams, like this is, I'm just drawing for a UDL which is in this shape, and you just reverse it, right? Just try to reverse this diagram. I want to change the color so that you can understand. So if you try to reverse this diagram and you then apply the load, then this entire system will be in compression, right? Or your bottom portion will never be in tension. That is what the beauty of precast beam and precast slabs, etc. We try to make a shape of that beam in a manner that once we apply the force, uh, the tension should not be there, or there should be a minimum tension which should not induce cracks in the structures. Are you able to understood this? Is it
Yes, sir.
fine? Yeah, perfect. Let me move forward. Okay, so this is the main thing which I want to tell you. The further, the primary purpose of any structure is to transfer from various element to the foundation, which you already know. And this you can read it nicely. I'm just going to highlight about the modern structures, and they are analyzed for the various loads, that's wind, earthquake, cyclone, blast loads, etc., right? So these are the various types of, apart from your live load and dead load, these are an additional load. Even if there is a snow, we have a snow load as well, right? And further, we are very much advancing in the material as well as equipment and technology, and thus it has resulted to go for more complex structure. Like if you see Al Burj, and now I think in somewhere in Middle East they are also making very long 120 kilometer of some magical city. So that is what our new technology has taken us to think more beyond structures which is beyond our imagination. Like even I think in somewhere in Taiwan they are building a structure which is more than a kilometer, right? So that is where we are now. I can see somebody. Sorry, you are not able to see my screen. Yeah, let me. Sorry. Can you see now?
Yes, sir.
Sorry. Yeah, sorry. So I'm just telling about the modern structures, and we are analyzing this for various kind of load. And now there is an advancement in the material, etc., which is leading us towards more complex structures. And if you Google it down about more advancement in the structural engineering, you will find there are several other buildings which we are coming into existence. And now for sustainable purpose, even we are more towards the timber structure. Now people are making building, multi-storied building with the timber structures. Like in Australia and Europe, they have started like 32, 30-story building from timber as well. So yes, we are progressing in a various forms, and technology is leading us to design and to go for more sustainable type of design as well, right? So next is the classification of the structures. So if we classify the structures, uh, they can be like they can be 1D, one dimensional, they can be one dimensional, two dimensional, and three dimensional. Like we try to idealize them, right? So analyzing like 3D structure is little bit complex. That is what, if you see yesterday, I have asked if you have a beam, right? This is a cross section of the beam, right? And then you run that beam all along, right? But what you do while you are doing the analysis, basically you are doing, right, you are idealizing your structure to the one dimensional form, right? You just ignore, or you can say you squeeze everything and you say, okay, let's this be a beam. So what you have done, basically you have squeezed the cross section of your entire, like this is your cross section. So you squeeze it down to the center of this particular beam. So you squeeze your dimension this direction, and this direction without compromising your analysis, without compromising your results. So although there is a slight change, and that you will understand once you go for higher studies in structural engineering, once you start doing using finite element. So we always say that once you apply a load on the top, right? So once you do that, if you remember, I think in your concrete design or any other steel design, you draw such shape. Do you remember this shape? Do you remember? So this, can you tell me what is this? Yes, Tom, can you write on a text box, what is this? What diagram I have drawn? What
Sir,
is this diagram?
can you
No, it's not shear.
can
It's
you
not
hear me?
shear. Huh?
Can you hear me?
Yes, I can hear you. Yes, go ahead.
Um, it's basically type of I forgot the name, but it's illustrating how the load is distributing from the top. There is at the middle the the bottom. So I really forgot. Yeah, something like that.
Yes,
That
it's a basically a stress diagram. Basically, yes,
yeah.
it's a elastic stress diagram, and we assume that your material behaves in a elastic range. So that is what we do. And once we apply a load at the top, we assume that this form of shape will be there for the elastic stress. So top will be in your compression, because this is compressive stress, right? And bottom will be in your tensile stress. And if we talk about the central portion, we say that there should be a zero stress at the center. This is what we assume, and we try to solve most of the problem in this way. But tell me, if there is a column and we applied a load on a center, what form of stress we call that? What type of stress it is? No, Ethan. It's a direct stress. So basically, if you try, it will the shape of that stress instead of triangular, because all part will be in compression. It will be straight away like this. This is P by A, straight away force over area, and that will be giving you a direct compressive stress. And this is a part of your bending stress. The one which we have drawn is part of bending stresses, right? So these concepts must be very clear once you advance in your structural engineering. Okay. And once you move forward with this, you will find that your top portion get more stresses. If you do FEM analysis of this, your top portion will be having a more different variation than your bottom portion. And that is what, once we do very detailed analysis of a beam, etc., we find those things with the higher and numerical analysis, numerical methods we use to solve such problem. Now at your stage, we are using a tool which you can solve directly the center line. But once we want to see the things across your cross sections, we generally use high mathematical tools in order to get more accurate results. So that is what they are mentioning here. And even you see the statement, if you read through it, the simplicity reduces the complexity and simplify the governing equation from 3 dimension to 2 dimension, or 1 dimension. And this reduction is achieved by making certain assumptions like Bernoulli's Euler kinematic assumptions in the case of beam theory. So this is your first question, which I want to ask you as a do it in your tutorial today. That is, write Bernoulli's, this one, Bernoulli's Euler's kinematic assumptions with reasons. This is your first tutorial question, with reasons, right? So reason them and how it implicate your analysis, right? So you have to critically think on this Bernoulli Euler kinematic assumptions in case of beam theory. Okay, did you get it?
So
Is it fine?
you want us to find the different assumptions and explain why we use them.
Yes, explanation is required. They will write uh, beam before bending and after bending remains same. So why did they want that? What how it simplify your analysis? You got me? Each assumptions, your reason of understanding that assumptions. That is what I need from yourself, right? Okay. So based on its observe the behavior under the load. So that is what they make these assumptions. They try to see how it is going to affect. They did some lab experiment and they found that whatever assumptions they have made, it's very close to the analysis, right? It doesn't affect the analysis too much, although it affects, but it doesn't go beyond a certain level, so that we can say, okay, we got in test, we got 10 kN of load, but while analyzing, we got like 12 kN of load. So anything higher side will affect, or maybe it is like lower side 9.8, but we will use certain factors that will enhance and that will make close to your experimental results. So that is how the factors and other things comes into existence. When you assumes your experiment result to be close enough towards your theory, you use certain amount of factors. So you just add it because of your assumptions, you use these factors, right? So I hope you understood this part of explanation. So that is what they are even writing. The simplification will yield results of reasonable and acceptable accuracy. This is how the experiment results and theoreticals are merged, or you can say correlate them wherever we do such development of the theories. So once you go for your any higher studies with project where the novelty or whether you are finding certain theories, you need to do set of experiment and then you need to move on. Okay, I just want to see if any chat comments and other things are there in order to process. Yeah, it's fine. Means, do you have any questions up till now? Did you understood? Is it fine? Can I move forward?
So
Perfect. Thank you. So these are all has been explained to you. I'll also tell you to refer this NPTEL. If you type NPTEL on your Google, you will get a website.
Sir.
Should I write a TUTE question very clearly? Okay, I will write them in a sheet and then I will upload it. Don't worry, Kevin. But it is good to train yourself that while I'll speak, the questions arises and then you need to write it down. I will write it for you. Don't worry. Now you are in advance, right? And later on you will be maybe honors or master student. So most of the things you need to understand and write it in your own way of understanding and then explain it. But yes, I will do that. Okay. So this is one form of structures, folded plates. Do you ever heard about folded plates? Did you saw any such structures in your life?
could this be such a thing as like a pile, what you call from, like they hammer it into the ground to support pipe structures or something if they want to do excavation?
Yes,
Piles.
they can. They usually make use of such thing, but even we make a very large roof with such structures, right? So let me see some example for you of folded plate structures, and then let me share it with you,
Like
and then
IPR
you can.
sheeting.
Did you saw your stadium where this football stadiums and all? And have you observed the roof there?
No. Which stadium, sir?
The one which is there on the sea point?
Oh, Cape Town Stadium.
No? Let me just show you some of the images. Then I think you will see that. I'm just searched some of the things. These are all like folded plates, right? So it's a thin short of structures which we try to balance. It just balance their own weight. Okay, so these are the structures which you see is nothing but your folded plate structures, and their analysis is quite different than what we usually do. These comes under the special categories of the structures, right? So can you see this?
Yes, sir. Yes, sir.
Yeah, so these are all like need a very special type of arrangements in order to analyze them. And basically these structures doesn't carry any additional load, but they only carry their own weight, right? Okay, so this is one thing which I want to show it to you in order to understand, and once you go you will also see how to design such structures. So basically I don't know whether you can see, yeah, this is the one. And these are the plate which you already know. These are the like 2D structural form, and then the whole we can go with the 3D structural form. Okay. If we talk about beam, you already aware of it. I'm not going to do in that detail. But yes, you will also come across with the curved beams in near future. And whenever we say beam, the loads acting on the beam uh, that will be vertical along wherever, like this is your axis, the load could be vertical on that axis or it can be inclined towards the axis. So that is what they are explaining here, that the load acting on the beam act in a plane containing the axis of symmetry of the cross section and the beam axis, right? So if you draw your beam like this, and if you draw you got the center of this. So now you got this center here, and now the beam axis, you draw this axis, and the load which act on this axis is nothing but vertical to this axis is, or inclined to this axis is nothing but your beam, right? So you can't tell if some load is acting on the axis of this beam. It act as a compressive in nature, but yes, the self weight will be down, right? So that we can't tell this beam as a column, but the nature of the axis of this beam. So the analysis of such beam will be different than what we usually do in the beam, right? So that things you will come across once you go for higher studies. I'm just explaining those things, right? So whenever we ask beam, you have to find out various unknowns in that beam, and that unknown will be your bending moment, your shear forces, and your axial forces. So these are the three unknowns in terms of your loading conditions. So that is ULS condition if we talk about ultimate load state. And apart from this, you have a SLS condition, that is service loading state. That is nothing but in that state you always find deflection of that beam, right? So whenever somebody asks to analyze complete beam, you have to look for your ULS cases, and in that ULS cases you need to find bending moment, shear force, and axial forces for designing purpose, and for the service case you need to find out the deflection, right? So then you have a complete analysis of the beam. If we call it complete analysis, you have a force, unknown forces to be find it out, and you need to also find the deflection of that forces, deflection of that beam. So that covers the complete analysis of your beam, and designing them for ULS and SLS is nothing but your complete design. So you can't ignore service conditions, because that service condition reflect your deflection component of your beam, right? So for complete analysis, force and deflection is required. And for complete design, you need to design it for the forces which are there in the system. And you need to also look for its deflection. Is it clear?
So,
Is it fine? Can I move forward? Anything you want to ask?
no, thanks.
Yeah, perfect. So there is also,
Sorry,
yes,
uh,
go ahead.
for ULS and SLS, so you're saying now we're gonna, what happened to we used to apply like a factor, a load factor. Is that a
Yes,
different situation?
that is what you have to use in this. Like whenever you do analysis, like whatever you did it at your diploma level, you get direct forces, right? Right? Direct forces like 5 kN is applied. But basically this 5 kN, whenever we talk about this 5 kN, in a real situation, it's nothing but you get it from your ULS condition, right? So whenever you are doing any complete design, definitely if you are doing design for your dead load and live load, so your dead load should be multiplied by a factor of 1.2, and your live load, or you can say imposed load, is multiplying by the factor of 1.6. So basically, this is what 5K incorporate these two factors while you are getting in your design. You got me? While you are doing the analysis, you always get a force straight away, but you never calculate it. But I think while you are studied the design component, you always ask that while you are analyzing them, you need to use ULS condition to get these forces. I'm clear to you? Is it fine?
Yes, sir. Perfect.
And whenever we call SLS condition and you are doing deflection check in your analysis, definitely that deflection checks already incorporated your dead load 1 times of DL and 1.1 times of DL and 1 times of imposed load IL. Okay, so your SLS condition in the analysis include your the load which you are taking there includes these things, right? Okay, so that is you need to understand where as a structural engineer that while analyzing your structure, you need to use your ULS condition. You can't analyze it for normal condition of the load which is acting on that, and then you design it. It will be disaster. Okay, so whenever you are analyzing in a real situation, you calculate all the loads which are there on the structures, use your factor, and once you have used your factor, whatever load comes, you analyze for those loads and then you design for it. You got me? Is it clear?
Sir. Perfect.
Perfect. So don't get confused on a side that this load has come and I have analyzed. No, you after getting your load, you need to go for the factors and then you move forward. Okay, so let's move on. This all you know. I'm not going in detail of simply supported beam, right? This is a continuous beam. You already know. You will also come across curved beams with certain radius wherever there is an architectural arrangement. How many of you have designed or design in the sense, I don't know about design, but how many of you have went for the analysis of the curve beam? Did you did it at your diploma level? No. That's a challenge. I think maybe sometime we need to include those things in our curriculum. Yeah, you need to also understand design of curve beams, design of analysis of curve beams. Yeah, thank you. Means I just need to know these things to include further while we do the revision of your modules. Perfect. Let's move on. You all know this truss, right? So Pratt truss, then you have Warren truss. These are all derived from the people and engineers who worked in the field for long, and all these truss are different and special in terms of their span arrangement, in terms of their force arrangement. So yeah, different types of truss can be used at different places, right? So this is different types of truss, and that is what they have shown. So these are all 2D structures, right? We analyze them 2D, although there is a, if you make it 3D, there will be another set of arrangement which is running on the another side of the truss. So generally we analyze one set, we replicate it on the other side, right? While considering the loads on the floor or on the floor of the truss, and then transferring them to the members of that truss. So that is what we need to understand. So we try to idealize them. Instead of 3D, we try to analyze all these truss in a 2D form, right? So this is what explanation is given. So this shows the plain truss that are made of short, thin members interconnected at hinge. So remember, whenever I always insist, whenever you have a truss, always think about axial forces, forget about bending moment and shear force diagrams. Please, whenever people ask about plane truss, make your mind very clear. You need to speak only about, people may confuse you while you are interviewing or while they are asking that, you just check your knowledge, right? So whenever they say the word truss is there, forget about BM and SF. Okay, just about think about axial compression and tension in that member. So never ever draw, means I have seen people are drawing bending moment shear force diagram for the trusses. Please don't do those mistakes. Those are blunders which you are doing with the truss members, because those are hinge, and if the member are hinge, they won't able to carry any moment at the ends. So there will be no end moments. There will be only axial forces on that hinge. Either it will be vertical force or it could be horizontal force, right? Okay, so those things you should keep in your mind while doing that analysis of a truss member. And they are in triangular pattern. And for the purpose of analysis, statically equivalent loads are applied at the joint, and these things you already know. Only axial forces, and they are constant all along the length. So this is what uh, definition of the truss says, that if you apply, although you have a load here, but whatever load you calculate, this is an excellent assumption that all along the length your force will be same, right? Although it reduces, if you do the real time real analysis on numerical softwares, you will see whatever load is here, it's keep on reducing till here and then again increases here. So but what we do, we take all along the same forces, right? All length of, that is what they are explaining. So now you are upgrading your knowledge, so definitely you need to understand that no, it's not like that. The forces keep on changing, but we made an assumption that the forces are same all along the length. Okay, the truss can have only hinged and roller support, right? In field, usually joints are constructed as rigid by welding. However, analysis were carried out as though they were pinned. So remember this, you already welded, but we always analyze them as a pin. This justified as the bending moment introduced due to the rigid joint in a truss are negligible. So if you see whatever bending moment comes, although you have welded, it will be negligible because of their triangulation arrangement. So this is a very real concept, and this will enhance your understanding about your process and other things. Truss joints could move either horizontally or vertically. So there is no rotation in that truss joint. This is also you have to remember. So they have only horizontal displacement and vertical displacement. There will be no rotation, right? So there will be no rotation, right? So either they can move horizontal or vertical. So there should be or if the member is like this, they can move in this direction or in this direction. So there should be no rotation in this member. So these things, these concepts should be very, very much crystal clear in your mind while you are solving the problem. Further, they are also explaining the space truss and how a member are subjected to only tensile or compressive force. Crane is an example of space truss. So if you see any crane, that is, you have seen the cranks in the crane, that is made of truss arrangement, right? So you can read this. I think I try to make many things more clear to you. Okay, and if you read these things, if you have any further questions, we can discuss on those things. So that this concept must be very clear while you proceed for your advanced design, else there will be always confusion in your mind why we are doing this. So you need to understand we made an assumptions in a manner that it won't affect the final results drastically. Okay. So another is a frame, and once the word frames comes into picture, the plane frames are also made up of beam and columns. And here they have mentioned the only difference being they are rigidly connected. So tell me, what do you mean by rigidly connected and hinge connected? Tell me, what do you mean by word rigid? Anybody?
I think if it's rigid, it will move as one when it's under load. It will deflect
Mm-hmm.
together.
Mm-hmm.
If there's like a hinge, obviously there can be some differences.
What differences? Tell me.
Um, I mean, there's more there's rotation in a hinge, but there shouldn't be in a fixed joint. So all the
Correct.
members will
Very
move.
correct.
All the
Rotation will be
members will
there.
move.
If I say the connection is rigid, let me take you through the whiteboard and let me explain you a little bit more on that, because this concept is also more very important. So I think I have to use new one. I don't know how to. Yes. Is there any? Yeah. Eraser. Let me use the eraser. Very poor eraser. Okay, let me use it here only. It's not a problem. The screen is very small, so I'm a little bit. Yeah. So if we talk about rigid, let's talk about. Uh, why it is not coming? Okay. So let's talk about rigid joint. So if we talk about rigid joint, what is going to happen here? If I try to rotate this member, right? If I try to rotate this member, whatever angle, whatever angle this member is going to rotate, this member, suppose this member rotate in this angle, the same angle is going to rotate in this member. That is the beauty of rigid joint, right? So if the joint is rigidly connected, both will be having a same. So if it is 30°, this could be also 30°. Okay. But if I talk about um, uh, hinged joint, like this is suppose hinged joint. So if I try to rotate, let me take another color. Yeah. If I try to rotate this member, right? I am not cutting. Yeah. If I try to rotate this member on certain angle, this won't be changing, right? This may remain same, because hinge hinge is trying to restrain it, but the rotation will not be transferred to the another member. Maybe it will slightly rotate that member because of joint, but it will only restrict this point in terms of not moving on this side, in terms of not going up, but it will not restrain the rotation of that. So if this member is rotating, definitely definitely this is going to be rotated. But remember, if this is there here, rigidly fixed, definitely this rotation will be induced on this member, but it will subsidize to the other. It will try to not rotate here because this is 0°. So that is what the beauty of rigid joint is. So this joint, if it is rotated and this is rigidly fixed, this will only affect to this joint. Are you able to understand this or not? Tell me. If you have any confusion, you can discuss.
Hello, sir. I've got a question or just something I want to clear up. So, in a rigid joint, does
Mhm.
the two segments of that joint become one due to the rigid nature of the joint? And with the hinge, it's almost like two separate points that is joined on that pin. Is that correct?
Yes, actually, that is what it happens. It will in the because in the hinge there is no moment resistance, right? It will not resist any movement. It will rotate. Okay, so that's the reason that both you can say they will treat it as a separate in nature. Okay, so it will not restrict the hinge will not restrict the rotation, but what is happening in the rigid joint, it will restrict the rotation. Okay, and whatever angular changes will happen here, the same angular changes will happen in other point, but that will not be the case in case of your hinge. You got me? I think I will share some of the diagrams which will make more clear. Maybe you can also explore it. You will understand the concept, right? I have given you the things, but you need to go through this. These things, I'm just taking you through this because I don't want any confusion while we are solving the problem. This could be your previous knowledge, but I just want to brush your things in order to move forward. I don't want to start straight away to the subject, right? Just to make your concept more clear. Yes, definitely. If you do that is what there is no, if it is joint is hinge, there will be no movement, right? Okay, but if it is rigid, definitely it will transfer your moment to the other end. That is what we do in moment distribution methods. Okay, then cofactor factors and some factors we apply, and then we get the moment transfer to the another joint or another section of the joints, right? Okay. Okay, so let's move on. Let me share the screen. Can you see it now?
Yes.
Yeah. So internal forces at any cross section of the plane frame members are bending moment, shear force, and axial. And what about in the hinge case? What are the forces?
Axial.
If I say
Eh?
only axial, correct. There will
Yes.
be no bending moment, there will be no shear force. So if it is a truss, there will be no nothing like that, only axial forces. But if it is a frame, you remember there are three unknowns. You need to find all these three unknowns. Okay. Uh, as against plane frame, space frames members may be oriented in any direction. In this case, there is no restriction of how loads are applied on the space frame, right? So these are some examples of space frames. Now equation of statics. You all know what is equation of statics. Tell me.
I think comes from Newton's law. I'm not sure which one, but force is equal to mass times acceleration. So it's all equations that have to do with out motion. So where there's a
Yes,
balance.
I agree. That is a Newton formula, and that is only a second law. And if we if we see, if we want to anything be in equilibrium, it says that summation of fx should be 0, summation of fy should be 0, summation of fz should be 0. Yes. And even summation of mx should be 0, summation of my should be 0, summation of mz should be 0. This is what we generally follow once we talk about static equilibrium. Okay. So if we apply force horizontal as shown in figure 1.7, then it start moving in the direction. That is what they are explaining. I'm not going to explain all this. You can read it. So yes, these are the equation of static equilibrium, and they have explained it. If you apply this force, it will move, right? Similarly, if you apply a vertical load, there will be a reaction from the bottom as well. So this is what they have explained. And if you see, a vector in 3 dimension can be resolved. That is what I have resolved the 3 forces, right? And also, if the resultant force vector is 0, then its component in 3 mutual perpendicular direction also vanish, right? Hence, above 2 equation may be written in the 3 coordinate direction as follows. That is what they have written, and this is what we have come across with equation of static. So whenever we say write down the equation of static, you need to go for it. Okay. So your next tut will be explain equation of static equilibrium, right? Explain equation of static equilibrium. So this is your next question, right? Is it okay?
Yes, sir.
Yeah, let's move on. So just read nicely and you need to explain it. These all has been covered in your previous thing. Is not to balance. Definitely it has, that is what, if you want to make anything in equilibrium, you need to balance the resultant. The resultant must be equal to 0. So the effect of the force should be 0. That is what we do in all our structures, right? We assume that the structure, unless until your structure is in equilibrium, you can't solve that structures. You start with making them in equilibrium, and then you apply this equation of statics in that, and then you try to get all its internal and external forces, right? So that this is how things work. Okay. So this is what they are explaining. Means you read it, you try to understand, and wherever you struggle, these are all covered, but I just want to take you through this so that once we start moment distribution, you don't have to end up like, oh, I don't know this, I don't know that. So these concepts should be very, very clear. Now here, if you see, if using the 3 equations, this is quite interesting, and that is what we have to deal with. Using 3 equation, we could find out the reaction at the support in a beam shown in figure 1.8. This is your figure 1.8 at the bottom. And after evaluating reaction, one could evaluate internal stress resulted in the beam. Definitely we will find like bending moment, shear force, and other forces. Admissible or correct solution for the reaction and internal stress must satisfy the equation of static equilibrium for the entire structures. And they must also satisfy equilibrium equation for any part of the structures taken as a free body diagram. So remember, whenever we are using this, and if we say our structure is in equilibrium, so in that case, any part of the structure should be equilibrium. That is what, if you remember how you have calculated bending moment diagram, you take any cross section and you apply equation of static equilibrium, you get the moment at that point, and that is how you draw a bending moment diagram. Similarly, you also draw shear force diagram by using same equations, right? So that is what they are saying, that they must satisfy, they must also satisfy equilibrium equation for any part of the structure. So once you apply the static equilibrium equation, it should be satisfied, or it should be governed at any of those things, right? So similarly, now the important things come. If the number of unknown reaction is more than the number of equilibrium equation, and that is what they have shown in figure this, right? If the number of unknown is more than number of available equation, then we cannot evaluate reaction, right? And we need to take help of some other things, right? So that is what they are saying. We cannot evaluate reaction with only equilibrium equation, and such structures are known as statically indeterminate. So this is quite important point. How you define a structure is statically indeterminate? This is your next question. How you define a structure is statically indeterminate. Okay, is it fine? Is it okay? So this is your question number 3. So you have to define it. Once you know that your unknowns are more than available equation, available equilibrium equation, because your equation of equilibrium is set number of equation which is available to you. But if your unknown is higher than that, then that structure is in statically indeterminate structures, and that is how you define them. You try to find all the unknowns in the structures and you compare them with the available equilibrium equations. So if the available equilibrium equation is less than your unknown, then it is statically indeterminate. Yes, please go ahead. Ethan.
I just know if we have a force that is, for example, going in the z direction, right? Um, are we do we not consider the fz, the forces in the z plane equal to 0 when determining if it's statically indeterminate or not? Because I see in this equation they say the moment regarding the z plane is equal to 0.
Yes, let me explain you. If you are only talking about 2D structures, right? 2D structures, okay? Two-dimensional structures, which is your beam. You have a one dimension like this, your y, right? You have your x, right? And whenever the rotation happens, it happens along z direction, right? That is what the rotation happens, okay? So that is what it is, mz. So at any point in a frame or in a rigid structures, you have available equation is only 3, like only 3. That is 2 summation of fx, like if you sum up all the x direction, summation of fy direction, right? And the one is the rotation along z direction. You got me or not, Ethan?
Yeah,
Is it
I
clear?
do, sir. Yeah,
But
it is.
if you have a three-dimensional structures, right? Let's take a three-dimensional structures. So now you have one more frame added, right? Now your structures become three-dimensional, is it? I'm adding this element as well in this structure, okay? So now you have a three dimension. So what is happening? You have X, right? You have a Y, right? And you have a Z as well. So all three forces will be there. Summation of Fx, summation of Fy, summation of Fz. Is it? Now there will be rotation of all along. There is one rotation along Z, there is another rotation along X, there is another rotation along Y. You got me? So you have a three more available equation, mx, my, and summation of mz. Is it clear to you, Ethan?
Yes, understood. So it depends on which dimension you're kind of looking at for the problem.
Yes, it depends on the
Okay,
coordinate,
okay.
like the coordinate which you are using. If it is 2D, definitely you always have a three equations which is going to solve your problem. Okay, but if it is 3D frame, definitely you have at each joint you get six equations. Got me? I'm
Yes, sir,
I'm
that's
I'm
understood.
ignoring twisting at this moment. I'm ignoring twist, right? Twist is nothing but rotation along its own thing. I'm just asking about joint. Like there is a one twist also there. If we put like two arrows, it is like a twist in this axis. But we are not taking distortion into effect. Okay? Do you understand the torsion?
Yes,
No?
the twisting motion
Yes.
of the beam.
Yes,
Yeah,
there is a rotating motion in the beam, but we are not taking, in most of the analysis, we don't use as it's become more complex.
right.
But it may be available. I'm not going to discuss at your level. At it will be more tricky, right? Okay. So let's fix these things. Okay. So I hope you understood this. So your third question is how you are going to define the structure is statically indeterminate. Okay. So further if we move on, it says that in such cases, if it depend on dimension, will it be statically indeterminate automatically 3D? I didn't understood your question. Let me read it again. If it depends on dimension, it will be statically indeterminate automatically in 3D. No, it's all depend. Like you need to know about the number of unknowns which you need to find it for your structures. It's all depend how many unknown forces you have and how many available equation. The one which we are writing here is a available equation, Tom. Okay. So these are the available equation to find out the unknown forces in your members. What are the unknown forces, Tom? Can you speak or can you write? If we talk about any frame, what are the unknown forces? Just write it. In frame structure, tell me what are the unknown forces. Just moment. You can't like moment, shear, and one more. Come on, yes. These are the three unknown forces in any member, right? In any frame member. Okay, and to get these unknown forces, you have available equations, right? So those are fx, summation of fx, fy, and summation of mz in case of your 2D frames. But if it is 3D frames, you have a six available equations. So if with the help of six available equation, if you are able to solve the frame, your frame is statically determinate. Well done. I am proud of you, Tom. Let's go on. Can we move forward? So you can see this, and you can see that here how many unknowns are there? 2, 1, 2, and here 1. So that is what 3. We have a 3 unknowns. So this is statically determinate. But if we see here, you have 1, 2, 3, 4, but you have available 3. So this is statically indeterminate. So I think we can stop here. I don't want to start with this, and we can continue at least in next class about 30 minutes, and then you can start your tutorials, right? So let's have a break. We can meet around 10:05. Is it fine?
Yes, sir. Perfect.
So let's have a quick break. Take some sip, relax your mind. Is it boring or is it fine? My lecture was okay.
No, it's good, sir. I
Yeah,
need
it's going
a
well.
refresher.
That's perfect. Means wherever you stuck, let me know that, sir, I didn't. You should be very frank enough to talk to me, right? Don't hesitate wherever your understanding is not clear, because I don't want to take you in a dilemma or mind where your mind is not clear and you're moving forward. You should be crystal clear, and you need to work hard, right, in order to do good in this. Okay, so let's take a break. My screen will be on. I'll just mute for a while, and then I'll come back at 10:05. Okay, perfect. Thank you. Okay, so everybody is there, or should we wait for another 1 or 2 minutes? Can we start?
Yeah, I'm here.
Yeah, perfect. I think I can see people are there. So yes, we can start. Okay, so the next is the static indeterminacy, right? And the aim of the analysis is to evaluate external reactions. That is what static indeterminacy uses, right? So once we use equation of equilibrium, we try to evaluate external reaction. Is this I have already told you, deform shape and internal stresses of the structure. So these are the three major component one somebody says, that is external reaction, deform shape, and internal stresses. And if this can be accomplished by equation of equilibrium, then such structures are known as determinate structures. So if all these three things you try to find with the help of equilibrium equations, then that structure is statically determinate, right? This already I have imposed this question, so you can explain very nicely this, right? And further it says that however, in many structure it is not possible only using the equilibrium equation, and those structures we call it as statically indeterminate. So I hope you understood what is statically determinate and what is statically indeterminate. The indeterminacy in the structures may be external or internal or both. So indeterminacy can be defined externally, it can be defined internally, or it can be defined both way, right? And you can call that structure is externally indeterminate if number of reactions exceeds the number of equilibrium equations. So if you want to define something which we call externally indeterminate, we need to use only equation of equilibrium and their reactions to define them. So they have taken one example. If you see this, the example which is below, have four reactions. So if you see this support is fixed, right? So you have a axial 1, you have a vertical 2, you have a rotation 3, and this is a roller, so you have one vertical. So altogether you have a 4. And what it says that whereas you have only 3 equation of equilibrium, so you have a summation of x, summation of y, and summation of f. So if you subtract it, 4 minus 3, you get 1. So this is externally indeterminate to the first degree, right? And similarly, they have shown another figure 1.10 and C and D that are externally indeterminate to 3 degree. So that is how we generally find it out. So if you see this, you have a three reactions here because of fixed support. You have another 3 here because of this, so you got 6, and you have only available three equilibrium equation, that is summation of fx is equals to 0, summation of fy equals to 0, and then summation of mz equals to 0. So these are the three. So 6 minus 3, you have a 3 unknowns, and that is statically indeterminate externally of 3 degree. This is what you need to write it out, right? Similarly, even for the portal frame, if you see this, you have a 3, you have another 3 unknowns, so only available is 3. So 6 minus 3, again, you have got this one. So did you understood this part?
Yes, sir. So this is a 2D structure,
2D,
right?
yes,
So we've
this is
got,
a 2D
yes.
structure. Yes.
So there's only those three. If we look at it from in this plane,
Yes,
there's only those three forces: X, Y,
correct,
and the Z moment.
correct, correct.
The Z
And if you
moment.
have,
So I just want to, sorry.
yes, go ahead,
For the Z
Ethan.
moment, I just want to clear something out. Just
Hmm?
how I'm trying to picture it. The rotation is almost is the rotation along the axis. So I mean around the axis. So it's
No,
going
it's not
basically
around the
into the page.
axis. No, Ethan, I think you have this axis, right? You have another axis which is Z axis, right? And now what you are doing, you are rotating each of your point for finding out moment about this axis. So that is why it is MZ. So you are rotating your taking a moment about your Z axis. So if you try to rotate, it will rotate like this, right? Okay, anything if you want to rotate on this beam, it will try to rotate, and the axis is along the Z axis. You got it? So that is why we write MZ. Okay.
Yeah, it's difficult to picture it. I'm
Difficult
just
to
trying to
picture
say,
it.
so if I was holding the beam between my two hands, okay, and I twisted it or turned it away from me along its, long length
let
angle.
me go to my videos. I think then I can explain it to you. Can you see me?
Not
Sir,
yet. I can only see the internet screen.
sir, is
Can
is
you
it
share
correct?
me?
Sir, we can't.
Can
We can
you see
still
that?
see the whiteboard.
Oh yeah, yeah. You can click on the screen. Click. Yeah, there we go.
Let
Okay.
me remove this whiteboard first application, and then you can see me as a whole, right?
Right, sir.
Yes,
We
Can you
can
yes.
see
see you,
me
sir. Yes.
full? Okay, so let's start with this. Can you see my pen?
Yes, sir.
Yes, maybe I can take some bigger thing. No. Okay, so if you see this, actually I just burned my hand, so I'm not able to drive to the campus. So that's the reason. So if you see this, if I push like this is your vertical force, okay? If I put this is a horizontal force, right? And while you are finding the bending moment of this beam, what you are doing basically, your axis is like this. So you are trying to rotate your beam along this axis, the axis which I'm pinning, right? You got me? So that is your Z axis. And you are trying to rotate everything along this Z axis to get your bending moment diagram. So that is MZ. Are you able to understand?
Yes. So the axis is kind of running into the page and out of the page
Yes,
of
you are
rotation.
running.
Yes.
Yes, this is the axis which is running in, right? And then you are rotating everything along this axis to get your bending moment diagram. You got me? You are rotating this beam along this axis, which is inside, right? Pinning in. You got me or not?
Yes, sir. I just wanted to clear that up. Couldn't quite remember.
Okay. So that is one. Your this part is your y axis, your x axis, and your z axis is like this. And for MZ, you are rotating every time your beam like this, and that rotation you draw it like a bending moment. I hope it is clear to you. Is it fine?
Yes, sir. Perfect.
Perfect. That's good. Let me share my screen again. Yeah. So this is how these things work. Means now you feel you read all these things. I think it makes sense and it will clear your mind more. So now you see you are going to the truss. Now truss is different from your uh, frame. And if you see these two figures again, They have said A and B. In these structures, reaction could be evaluated based on equation of equilibrium, right? However, member force cannot be determined based on static alone. So if you see 11, if one diagonal member is removed or cut from the structures, then the forces in the member can be calculated based on equation of equilibrium. So that is what they are saying. Thus, the structure 11.1.11 and be internally indeterminate. So now, if you see your top structure, it is externally, and now they are explaining internally, right? So for the internal purpose, they say that if you see this truss, what is going to happen, right? You have 2, you have 1, so you get 3 and 3. So you externally this structure is perfectly fine, right? But if you want to try find out the forces in these members, now the problem is with these members. For the beam, you don't have problem. If you get all these forces, you start finding out the member forces, right? But for the truss, if you see, 3 members are connected in this case, and now the problem started, right? So that's what it says, that if you can only remove one member, now you can find out at every place you get 2 equations, like because this is hinge, you need only 2 equations to do that, right? Okay. And that is what say that if you for all other places, you start using summation of fx and summation of fy, you can get all the member forces. But if this member is there, you can't get all the member forces. Is it okay? Are you able to understand? So this structure is internally indeterminate of 1 degree. This is what they are trying to explain. So this we call as a redundant, right? So many redundant are added in a truss members, right? That make the structure internally indeterminate. So while solving those indeterminate truss, you remove some of the member, and then you start your analysis, and later on once you get all the member forces, you can get the force for that particular member. This is what we will see once we start with our virtual work problems, right? So that is what it is explaining. The truss frame member shown is both externally, sorry, I've just made a wrong, right? It is only 2 available equations, sorry. There are 3 unknowns with 2 available equations. There is no moment equation, right? To get a moment at this point. So it is externally and internally indeterminate. Okay. Further, they have shown the space one, and they try to explain, and you just go with this. The explanation is given here. But in order to easily state whether the structure is internally or externally indeterminate, they have used certain equations, right? So let's see those equations. I don't know whether you have come across with these equations while you are doing your um, previous analysis courses. Oh my word. Ethan, did you know statically determinate or indeterminate structures?
Yes, sir. We did come across the concept, and we spoke about how to kind of solve, like you just explained now. But we haven't.
Mhm.
Personally, I haven't seen this equation.
Oh, okay. So up till now, I think you have dealt only with the determinate structures where you can easily find reactions and the member forces, because using only equilibrium of static thing. So did you solve any indeterminate structure in your previous knowledge?
So not that I can recall, it was all or
What do you and
determinate.
beam? No, I'm asking determinate structures, like where the unknowns are more than the available equation. Did you solve any such questions?
So we came across a couple, but then we just kind of brushed over it because I don't know, for time restraints or something, but we haven't actually worked through a problem of an indeterminate structure.
Okay, so in this course, definitely you will be. Yes, I think yes, you are right. I think you have solved some of the indeterminate, but not that extensively. But in this course, we will mostly dealing with the indeterminate structures where you need these things to know whether how much degree of indeterminacy is there in the structures, and then you need to work with that indeterminacy, right? So let's move on. Uh, so far it's mentioned whatever we have seen degree of determinacy with the with inspection, like we observe, we know, and that is what we did, right? So that is what we do while we visit a site and we see the structure. We ask the consultant or another other that okay, how you have designed this structure, what are the conditions, and you see the all the members. Oh, okay, this is statically determinate. Then you also observe how they have analyzed, what method they have used. So these are all checks which you usually do on the site while you are inspecting the site, right? Once you have a good experience, so while you go on the site, you see everything visually, right? And later on, once you come to the office, you get the design drawing, and then you see other aspect of the things, right? But while you go to the site, by viewing the site or by observing the site, you will knowing that okay, this structure is determinate. Okay, so simple analysis can solve this problem. But while again seeing some complex trusses, etc., and then you see okay, so this is a little bit complex. I think they need to do some special analysis methods, and then you try to see what method they have used, right? And what is the degree of indeterminacy in that structures. So now let's see how they have calculated. So they started with the planar stable truss. So for a truss member, mostly in case of truss, there is a problem because there are so many redundant added in order to maintain the stability of the structures. Because and why that is needed? Because what is happening in a truss member, the members are long, and the major issue is slenderness ratio, SR ratio. And to increase the slenderness ratio, they try to put some of the redundant in between, try to reduce the length of the member so that it cannot buckle, right? So that is the main solo purpose, that they add more members in between of truss. So that redundancy enhances the stability of the structure, but yes, the calculation of the force becomes a little bit problems, right? So that is what they try to explain you here. So considering planar stable, let the having m members in the structures. With that m members, there should be j joints wherever they are joining. Let the unknown reaction component of the structure be r. So whatever the unknown reaction component, we will dealt with r. Now the total number of unknown, how many total number of unknown is m plus r, like the member forces and the unknown reactions, right? Further, at each joint, we could write two equilibrium equations. So it is a hinge, and definitely at hinge, I know that I can write summation of fx, two equations, right? That is what they are explaining here. So that is nothing but summation of fx and fy. That's why they multiply with 2, right? So that is why they multiply by 2. So the total unknown is m plus r. And if from the total and unknown you minus 2j, that is how many equation you have in that structures, that will give you the degree of indeterminacy of that structures. Did you understood this formula? Did you understood it?
I've got it, yeah.
Yeah, perfect. So now this is two-dimensional. So I is nothing but for this is you can say a planar stable truss where you just draw this planar. But if you have a beam, so beam there is a little bit criticality, because in beam you have available like three forces, right? So there is a reaction, and C is nothing but like if it is hinge at some point you use 1, and if it is a roller at some point you use 2, and if it is um, C will be 0 if the structure has no geometrical instability, like if it is a plane and you don't have any hinge in between or any roller in between. So you have a plane, so this C becomes 0, that is R minus 3. So R minus 3, if you take as a general, R is nothing but number of unknown reactions, and 3 is nothing but available equations. So now they have added C in this, and that addition is nothing but if in a beam, suppose you have a one beam like this, and you have a one roller here like this, right? So what has happened in this case, if you use this, so you have a 2 here, here, and 1 here, right? So in this case you have a 3 unknowns, right? So R is 3 and you have a 3 available equation, it is 0, right? Now if you add one hinge suppose in between, so if you add hinge, that will give you one more. So one more equation you will get. This C is nothing but while adding this hinge, you will get one more. And if you add another roller here, you will get another uh, two equation at this point. So that is what they say, that if we add something in two-dimensional beam, as we know that R minus 3 is equation available, that will clearly define the internal, indeterminacy of the structures in case of the beam. But beam, we generally solve it quickly because we don't have any such issues. But yes, once the hinge and roller added in that beam, then this equation is very effective, right? So three-dimension truss, again M plus R, but at each joint you have a 3 available equations. So you see you have a truss, so Z is also going to be added. So that's what it, each joint you have M plus R, M is number of member, R is reactions at the supports, and J at each joint how many equations are available. So these equations you can use directly into your formations, right? I will definitely give some more. Yes, Matthew, you can speak.
Cool. So, hey, just quickly, um, these joints, does that include the support joint? The joint
Which
at the,
one?
at a,
No,
that joint at the support.
R is nothing but your reaction at the support, right? And then C is nothing but if you see in this is nothing but your number of extra available equations. So if you provide anywhere that hinge in your beam, it will give one more equations, right? So that is why in this case 3 is always available with you when it is two-dimensional beam, right? But C is an additional extra equation available if you have a roller anywhere in between, or if you have any hinges in between. You got me?
Yes, sir. I understand that. But now, for example, on a truss, uh, at each support on a truss, depending obviously how it looks, there could be it could be a joint as well of members.
Yes, definitely. But that support will be treated as a reaction. Okay, that is not a joint. Joint is just a joint, hinge joint. You can't
Okay.
treat it as a support. You got me?
Yeah.
If anywhere in the trust you got and any other support, that will treat it as a unknown reactions. Remember that. Okay. Let me clarify you. Now, suppose this is your trust, right? Okay. You got one support. This is a support. You need to have a reaction, right? This is another one. Okay. And suppose you make another one and you put another support here, right? So now you are available with only one joint, okay, J, but you have three reactions unknown. Is it okay?
Yes, perfect. So 5 reactions unknown.
Yes. So these are all frame equations. So that is what you have to see for. So let's see problems. And if you see this problem, this is a continuous beam. Can you use this equation and solve this and tell me what will be the I for this particular beam, this continuous beam? Just do it and tell me. Once you finish, you type your things in the chat box. I is 2. 1, 2, 3, 4, 5. Minus 3. Any other? Anyone else? No one. Kelly, did you got any answer? James? Let me do it polling. I just want to need any of you got 0, 2. Yes, just answer me yes or no. I just want to see how many of you got 2 I is equals to 2. Matthew, you can also respond 1. I is equals to 12. 12 or 2?
That's for the next one, sorry.
Oh, next one. Okay, perfect. I'm just asking for this. Yeah. So 4 of them. 2 yes, 2 no. I think others just on this and 3 no. So those who got another answer, can they type on a chat box what they got? So only 5 of them, 5, 2, 2.
Sir,
Yes,
sir,
Ethan?
for C, do we multiply the 2 by the number of roller supports we have?
If you see this, you have an axial. So at this point, you have horizontal reaction 1, right? Okay, then you have a vertical, then vertical, then vertical, and then vertical, right? So you have a five unknowns, right, with you, is it?
Yeah,
And now
yes,
how
sir.
many available equation is summation of fx, summation of fy, and then summation of mz. So you got 3 equation available for you. So that is 5 minus 3.
Oh, I see now. Okay, cool. Thank you, sir. Thank you.
Okay, so you got this one. And if you see the plane frame here, so you got 3 here, you got another 3 here, right? And you have available how much? Again 3. So for next case, it will be how much? If we talk about indeterminacy, I, if you see a plane frame that is 2-dimensional, it is 6 minus 3. So it will be 3 for plane frame. Okay. And now for this one, how much you have? You have a 3, 3, 3, right? So you have a 9. Ethan, for which one you got 6? For C, yes. So I hope this thing is clear. Let's do the last one. I think this is kinematic indeterminacy. And I think this I will take in the next lecture, and then we will start different one, because this needs more concept. I don't want to mess with you most of the things. This is very short topic, so we will complete it and move towards your movement distribution in your next class. So what I suggest, whatever questions I have given, the 3 of them, you read, you write it. I'm creating one submission that is informal one. So you need to write and you need to just submit that part in that particular once you finish this class, right? And I will just quickly go through that. So I will just create a submission for the first informal assignment, and while you are doing that, I will also going to post some questions for your getting indeterminacy of the structures. Okay. So let me, you can start with these 3 questions which I have imposed to you. And that is the very first one. Let me go. You have to need to do Google as well. And you have with you almost 40 minutes. And in that 40 minutes, try to answer these 3 questions, right? And submit it. So the very first question I want to frame it for, I think somebody has asked, uh, what do you understand from Bernoulli's Euler kinematic assumptions? Okay, so this is a question which you need to explain, right? Explain. So this is the first one. And the next one is your, I've already given. The next one is your explain equation of static equilibrium, right? Explain equation of static equilibrium. Okay, this is Q2. Now the third one, you can expect such questions while you are writing your sum test. I'm just making you prepare for such things, right? Question number 3, how you define structure is statically indeterminate, right? Okay, so this is your third question. So you can write it down. I think I have already uploaded this notes in your lecture. Okay, you can go through it, and I am available. I'm here whenever you have any problem. You can discuss. I'm here up till your class ends, so I'm not going anywhere. So I'm sitting here only. So my suggestion is I'm just creating one assignment where you can submit. While you do that, take a snapshot, just submit with your name and roll number and even your class group, right? Okay. Anything you want to ask? So if not, the floor is yours. I want to see there are 27 and I want to see how many can submit by 11:25, right? So that will show the efficiency of this class and your eagerness to learn the subject. It's not about, that is what online thing is. But once my hand is okay, I'll try to be on campus, and that will be more fruitful classes. Please move question number 2. Okay, I'll move it to question number 2. Explain equation of static equilibrium. Yes. Is it fine? Can you see it? Paola?
How must we submit our answers or whatever?
Yes, you have to submit your answer by 11:20, 11:25. Okay.
On what?
And what?
Where should we submit the answers? Just in the chat?
No, not in the chat. I'm creating on Blackboard. I will mark in the sense I will informally check everything. Okay.
Oh, okay.
I'm just creating one informal submission, and I think you will have the link with you on the box where you can submit your things, right? Okay. Question number 1, Ethan. Okay, let me move it to question number 1. Let me stop recording. It is not, yeah, this is your question number 1.